Phenomena of surface tension known as capillarity. Probably you know this, you have already read at school level, that if in a beaker or in a container of liquid, if we dip a tube, we see that liquid rises in the tube. Sometimes liquid rises in the tube from the level of the liquid in the container, in the tube. Who is responsible for rising of that liquid in the tube, or who holds this extra amount of liquid height in the tube? That is purely the phenomenon of surface tension, or the surface tension force is responsible for that. In some cases we have seen that liquid, if there is a container containing liquid and a tube is dipped into it, the liquid doesn't come up to the surface of the liquid at the container. It goes up to a height which is lower than the height of the liquid level in the container. So these two phenomena are known as capillary rise and capillary depression. Let us see that. Phenomena of capillarity. Phenomenon of capillarity. Okay. Phenomena of capillarity. What is this? Let us see this. If we take for example water, let this is water or any liquid I can tell, and if we dip a tube, you will see the water comes, take an interface like this. An additional height of water comes like that, is raised like that. Now who is responsible for holding this additional height of water? For example, here the pressure is atmospheric pressure, but here the pressure is the height of this water column. Let this height be h. So who is responsible to make this disbalance of pressure? That means there must be some upward force which is counterbalancing this pressure, or other way we can tell there must be some upward force which can hold the column of water which has been raised, and this force is the prime cause of raising the liquid through the tube from the level in the container. So this is known as capillary rise, capillary rise, and this happens to those liquids where adhesion between the liquid and the solid tube, this is the solid tube, is more than the cohesion. This happens. For water in a glass tube, the adhesion is more than the cohesion. So this is marked in case of water in a glass tube. It is found in some other cases, for example, mercury in a, rather here you can take mercury in a glass tube. That means if you have mercury in a trough and put a tube like that, you will see the mercury will not come up here. So the mercury interface will go like that. So there will be a mercury like that. So this place, in this space there is no mercury. So therefore the mercury level here in the container up to this, but mercury will not come up to this. That means what is the force that is responsible to create this disbalance? That means to make up this. Here the pressure is atmospheric pressure plus this height of the liquid, but here pressure is atmospheric pressure plus this height of the liquid. Let this is the depression. This height is the height depression of the liquid. Here it is the rise. So that means this is the depression. So here the pressure is less. So there must be some additional force in the downward direction to make a balance between these two. What is that? That is the surface tension force. What happens physically, now let me explain. Because of this adhesion being more than the cohesion, the liquid particles are dragged along the solid surface, by virtue of which the liquid is pulled. Depending upon the surface tension force, the liquid height will be maintained. The liquid height will depend, or depending upon the surface tension force, the amount of liquid will be raised. Let us consider this amount of liquid raised up to the height h. So under this condition, if this is the interface, we can show that in this interface here, the surface tension force T acts. Surface tension force. This acts throughout the periphery in the linear element with an angle. Let this angle is theta. That means surface tension, the direction of the surface tension, this is tangent to this surface with this vertical surface of this tube, let this angle be theta. This angle is known as area contact angle. Area contact angle. So now this is the force. That means you see that if we take the component of this force in this vertical direction, that balances the weight of this column. You write this. Now T into, if we consider the diameter of this pipe is D, big D, diameter of the pipe is D. So T is equal to pi D into sigma. So therefore pi D sigma cos theta must balance the weight. If we neglect this portion, only take this cylindrical portion of the liquid weight, so this will be pi d square by 4, that is the area times the height h into rho in volume into g. So this is the weight of this column of liquid. This is being balanced by the vertical component of the surface tension force. This gives rise to the value of h as, what is h? 4 sigma cos theta, 4 sigma cos theta, 4 sigma cos theta divided by what? By rho g d. Similar expression you will get for the capillary depression. The physical phenomena is that in this case cohesion is more than adhesion. So for liquid where cohesion is more than adhesion, that is adhesion is less than cohesion, then what happens? The liquid molecules will crowd within each other, and if their intermolecular forces drag them out to come out from the free surface. That means they come below the free surface, and what happens? The surface tension force will act in this direction. So therefore you see the vertical component of this surface tension force act in this direction, which is added up with the pressure of this less height, and will make the balance of the pressure here. And if this be the h, the difference you can find out is the weight of this column of liquid, which is an imaginary. It was not there. If this column, this liquid could have come up to this column, so this weight could have balanced. So from that balance you get the same expression h. So here one interesting phenomena comes, that the capillary rise or the capillary depression h is inversely proportional to d for a liquid of a particular value of sigma. So therefore this is observed only in small diameter tube. As the